applications of differentiation to kinematics. We're really just going to do some application questions today. Kinematics refers to the position or movement of a particle or object around an origin, but again you have a position equation and then we can find quite a bit from there. Average velocity, so that's how it's different to instantaneous, is that word average, is where we're finding the rise over run or gradient between 2 points on our original position function. Instantaneous is where we would find the derivative and then calculate the instantaneous velocity by subbing in an x or often t value. You'll see in a moment how average speed can vary from average velocity. They can often look the same, they can occur to be the same answer, but they can be quite different. So just be really careful with the difference between average speed and the average velocity, and you'll see that in one of our questions later on. Average acceleration is our rise over run, or our gradient between 2 points on the velocity function. So that is where you found the derivative, the velocity, and you're finding the average acceleration by using that and two various t values. Instantaneous acceleration is actually the double derivative, lots of notation and ways to write that here as well. But you can see that in my little kind of explanation on the right here. Our original function relates to position, our first derivative is velocity, and our second derivative is acceleration. So the derivative of velocity is acceleration. For some reason these questions start using x instead of y for the position function, and then t is our kind of variable. I know that's a bit confusing, just stick with it and hopefully it'll make some sense as you practice it a bit, but just read questions really carefully through this section. So this is a little recap question to just check that we're on the right page in what we're doing. So the average rate of change, we know that means we need to sub in our x values of 2 and 3 to our original function, giving us 2 squared plus 2 times 2, which ends up being 8, and 3 will give us 9 plus 2 times 3, which is 15. We then find our rise over run for those coordinates, so 15 minus 8 over 3 minus 2, and that's just going to come out as 7. The average rate of change between 2 and 2 plus h, so we actually have the coordinate 2, 8 already. I'm just going to find out what f of 2 plus h is, so this is slightly different to how I've done it in the past. So that's 2 plus h squared plus 2 bracket 2 plus h. Let's see if I can fit it all here. 4 plus 4h plus h squared plus 4 plus 2h. That comes out to be 8 plus 6h plus h squared. And now using our rise over run, so we do have a kind of coordinate here of 2 plus h, and 8 plus 6h plus h squared. So rise over run, 8 plus 6h plus h squared minus 8, so that's our y2 value, or y1 value, however you want to think of it. And then we've got this 2 plus h minus 2. So you can see quite quickly we're getting some cancelling going on. We can factorize out an h from our denominator and our numerator, so that leaves us with the average rate of change will be 6 plus h between 2 and 2 plus h. So that's the kind of first principle stuff, just working that through as best we can. Find the instantaneous rate of change at x equals 2. So we could actually just sub in h as 0 at this point, but let's just do it by finding the derivative, which is 2x plus 2. I'm going to sub my value of 2 into my derivative, giving me 2 times 2 plus 2, which of course is 6. So as we already knew, our instantaneous rate of change when x equals 2 for that function is 6. Moving into our application questions, a ball develops a leak and decreases in volume at a rate of this. I don't want to read all that out. What is the initial volume? So that is where we would have v of 0. So we could write out a little bit of working here if you really wanted to. But hopefully you can see that that would just be 600. We're not given the volume there. If we're talking test marks, this would be 1 mark and this would be 1 other mark. So stating that you understand to make t 0, that's what initial volume is referring to. That's a really good thing to just show in your working. I mean, you could also write all this out to show that as well. For how long will this model stay valid? So we're just going to use our values here or here. I mean, it doesn't say decimal, so I'm going to use my exact value. Obviously, we can't have a negative t value, so we would kind of get rid of those. But yeah, we would say how long is the model valid? So we'd say where t is an element of, I'd probably include 0 here because we have actually found that exact. Actually, we're told at the start that it's when it's greater than 0. So I'm going to do a curve bracket of 0. And I would write 200 times 8 root 10, 10 minus 25. Didn't leave myself much space there. And that would be another curve bracket as well. So that'd be it. You probably could do it to exact, actually. I think I'd probably do a square there because the volume would be exactly 0 after that amount of time. So this is your more classic kinematics question. A particle moves from position O, the origin, a distance of x centimeters at time t seconds following this function. So we're already getting this kind of slightly strange setup where we have xt, where t is in time in seconds, and x is our position. I've got a little graph on the right there that I'm going to keep coming back to. I'll try and explain that a bit more in detail as we go as well. So find the initial position. So that's not too bad. That's when t is 0, subbing that into the original equation, which would give us just straight up 6. So both of these would become 0, so we're just left with 6. That means it starts 6 centimeters to the right of the origin. So that positive 6 value means we're actually to the right 6 centimeters. Find the initial velocity. So the instant velocity is mentioned. We're finding the derivative, which in this case is 2t minus 7. And the initial velocity is when t is 0, giving us negative 7 centimeters per second. So that means it's moving to the left 7 centimeters per second at the start. So it's moving in this direction to begin with. When is the velocity 0? So that is where we'd make our derivative function equal 0. Remember, the derivative is our velocity function. So t equals 7 over 2 or 3.5. I kind of didn't want to have to do all this at once. So subbing that 7 over 2 into the equation, we'd have our cas for this. It comes out to be negative 6.25. So let's just talk about what's occurring here. So what we found is it started at this point here, 6 centimeters to the right of the origin. It then moved 12.25 centimeters to get to this point here. So that means after 3.5 seconds, it was at negative 6.25. So that's an important point. And we haven't found this yet, but it's going to come up in a little bit. We need to find out what its finishing point is, and that is when, after 4 seconds, so you're going to see that in our question F, but if I subbed 4 into this original equation, I'd get the answer negative 6. So this is occurring when t is 4, this is at t equals 0, and this is when t is 7 over 2 or 3.5. All right. What is the instantaneous velocity at 4 seconds? So that's just subbing in 4 to our velocity function. So t times 4 minus 7, which is just 1. Determine the average speed for the first 4 seconds. So that's the distance traveled over the time taken. The distance here from here to here is actually 12.25. So hopefully that's making sense. It's kind of gone 12 to here and then another little 0.25. It's then got another little 0.25 where it's come back, so it's actually traveled now 12.5 all over 4 in the first 4 seconds. And that comes out to be 3.125 centimeters per second. So this can be a little confusing. What is the average velocity in the first 4 seconds? This is different to the distance over time function. So we had to calculate the total distance there. And because it turned around, we got a slightly different distance value to just these first 4 seconds. We're just looking at the position of these various values. So that would be 6 minus negative 6 over 0 minus 4. That's 12 over negative 4. And that would be negative 3 centimeters per second. So average velocity is slightly different to average speed. They can be the same, but if something has a turning point and it's turned around in this instance, then they could get different answers as well. So tricky question from the textbook. If you want to move on, you can, but if you want a bit of an explanation of this one, let's have a go at it. Two particles are moving along a straight line, both so that their position x1 and x2 centimeters relative to a fixed point P at any time t. Seconds are given by x1 equaling t plus 2 and x2 equaling t squared minus 2t minus 2. Find the time when the particles are at the same position. So we're just going to make our equations equal each other basically. So t plus 2 equals t squared minus 2t minus 2. And if I equate these, we're going to get minus 3t minus 4. Factorizing. So when t equals 4 and negative 1, we generally don't go backwards in time, so we would say that t cannot equal negative 1 and t just equals 4. Find the time when the particles are moving, that's it. Find the time when the particles are moving with the same velocity. So the velocity of my particle 1 position is the derivative, and that's just going to be 1. And the derivative of my second particle is 2t minus 2. If I equate those, I end up with this, minus 3. So 3 over 2 equals t. So when t is 1.5 or 3 over 2, we have the same velocity. And that's it. Bit of a weird question in the phrasing, but that's all we have to do.